Topic 3, Day 1, Pythagorean Theorem. So the Pythagorean Theorem only applies to right triangles. So if you think I need to use the Pythagorean Theorem, always double check that whatever triangle you're using is actually a right triangle. And we can know that for sure because we have a little square at the corner there, or maybe in the written part, it specifically says for this right triangle, whatever. Now the Pythagorean theorem states that the square of the hypotenuse is equal to the sum of the square of the legs. So a couple things to remember. Your hypotenuse is always your longest side, and it is always opposite of the right angle. Okay. Once you know which one is the hypotenuse, the other two sides are your legs. They make up your right triangle, right? So if we know that our right angle is right here, then this side is a leg and this side is a leg. Now, what's really cool about the Pythagorean theorem is there are actually over 100 proofs that show why the Pythagorean theorem works. But here's just one relatively simple proof. So in the middle, we have a right triangle that they've labeled A, B, and C, where C is the hypotenuse. And C happens to be made up of 5 units. And what they've done is also indicate what is 5 squared, or 25, right? So this red square here represents C squared, right? Because that side is C, this side is C, C times C is C squared, right? Since C is equal to 5, 5 squared is 25. Similarly, our yellow square is equal to B squared, and our smallest blue square is equal to A squared. And when we add up the values, right, 9 plus 16, it equals 25. So this is like a visual, right, area-based proof to show that the Pythagorean theorem works. Now, Pythagorean triplet is 3 positive integers of A, B, and C such that A squared plus B squared equals C squared. So it's essentially when A, B, and C are positive integers. Any multiple of Pythagorean triplets are also Pythagorean triplets. So they're kind of useful to have memorized, or at the very least, they're familiar numbers that you'll see relatively often, right? The most common of which is 3, 4, and 5. So if you look at our proof from above, our sides were 3, 4, and 5, and they were all whole numbers, which makes them Pythagorean triples. But what's cool is that if I multiply 3, 4, and 5 by 2, then I get 6, 8, and 10. And what's really cool is that 6, 8, 10 is also a Pythagorean triple. Now, we should always reduce to simplest radical form. So a radical, or like a square root or any kind of root, is said to be in its simplest form when the number under the root sign has no square factors. So for example, if you take the square root of 72, one of the factors of 72 is 36. And 36 is a square number, is a perfect square, right? 6 times 6. So we can take the square root of 36 and we get 6. And the square root of 2 remains because 2 does not have a perfect square factor. Answers should be in simplest radical form unless it is specified otherwise, okay? And in the example that we're going to go over, I'll show you how we can get it into simplest radical form. So our first teacher example, determine the value of y, leave your answer in simplest radical form. Number 1, can I use the Pythagorean theorem? Is it a right triangle? Yes. Number 2, we have to identify A, B, and C. C is always your hypotenuse. So here I find my right angle. I look at the side that's opposite. That is my C. The rest are A and B. Then I can plug it into my Pythagorean theorem. A squared plus B squared equals C squared. So in this case, that would be 8 squared plus y squared equals 12 squared. and I'm going to subtract 64 from both sides. Y squared equals 80, and I need to take the square root of both sides. Y equals the square root of 80. A couple of things. Number one, when you take the square root, technically we should get plus or minus 80, right? But since we're solving for side lengths of triangles, we cannot have a negative value to represent a side. So we always only use a positive for Pythagorean theorem for like side length geometry kinds of problems. Second, the square root of 80 is not in its simplest form because there are perfect squares that are factors of 80. And there's two ways that you can go about simplifying this. Number one is if you know all of your perfect squares, right? So those are your numbers 1, 4, 9, 16, 25, 36, 49, so on and so forth. And you can figure out what is the biggest perfect square that is a factor of 80. In this case, it's going to be 16 because 16 times 5 equals 80. Then we can rewrite it as, and then take the square root of 16, and we get 4 square root 5. And we can always use a calculator to double check. We'll find if you put the square root of 80 into the calculator, it's approximately equal to 8.94. When you simplify it, the value should stay the same, right? It's just another way to write the same value. So 4 root 5 in the calculator is also approximately equal to 8.94. Okay. The other way, if you don't know all your perfect squares off the top of your head, is actually just to go through the prime factorization. So what any two numbers that give you 80, so 10 times 8, for example, and then just going to keep going until I only have prime numbers. So 2 is a prime number, 5 is a prime number, 4 times 2, 2 is a prime number, and then 2 times 2. And then I'm going to rewrite it as 2 times 2 times 2 times 2 times 5. And then any pair of the same number is going to be pulled out. So 2 times 2 is 4, and then 2 times 2 is 4, and then 5. And then the square root of 4 is 2. The square root of 4 is 2, and then 2 times 2 is 4, 4 root 5. Okay. Go ahead and find the value of the third side and have it in simplest radical form if necessary for student example number 1. Okay. So here's our second teacher example. Again, it says to solve for x. Leave your answer in simplest radical form. So if I want to solve for that side, then I need to figure out what that middle value is. And in order to figure out what that one is, I actually need to start with this leftmost right triangle. So I see that both of them are right triangles. I'm given two sides of my left triangle, which lets me solve for this the middle side. And then once I have two values, two side lengths of my right triangle, I'm going to be able to solve for x. So let's start with triangle number 1. I know that 9 is my C because it is opposite my right angle, and I can label my A and my B. So then I have 5 squared plus B squared equals 9 squared. 25 plus B squared equals 81. And B squared equals 56. Now, I'm going to be using the square root of 56 in my Pythagorean theorem for the second triangle. So here, since this is an intermediary step, I don't actually have to get it into simplest radical form. This is not my final answer. So I'm going to pause here, and I'm going to label this side to be the square root of 56. And then I'm going to move on to my second triangle. And what we need to be careful about here is a leg for one side is not necessarily the leg for my second triangle. So here we'll find that our right angle makes our square root of 56 be our C value. It is the hypotenuse for our right-hand triangle. And then 6 can be A, X can be B, and then we'll have 6 squared plus X squared equals the square root of 56 all squared. Gives us 36 plus X squared equals 56, and then subtract X squared equals 20, square root both sides, X equals the square root of 20. Now, since X is what we're solving for, we do need to get the square root of 20 into its simplest radical form, right? If I think about its factors, this can be split up into the square root of 4 and the square root of 5. And I know the square root of 5 is a prime number, square root of 4 equals 2. So my final answer is 2 square root of 5. Go ahead and try student example number 2 on your own.